Hello, this is Claudio from expertfea.com with a live stream, this time with simulating gears in motion. So let me firstly share my screen. Right, a quick reminder about my website, expertfea.com, where you can find lots of simulations, books, and FEA support, which can put you very quickly directly in contact with me, and I will support you for complex FEA. So today we're going to be briefer than other times. Let me save this as stream 25 with the today's date 06 or June. Okay, June 16. I have done this simulation before, so it should be no problem. I have it in my face in case I get stuck, which is hardly an opportunity. A very quick way to simulate this. I will spare you the geometry troubles and seed modeling. Let's see if I can find the original file in order for you to understand how much I simplified the geometry for this simulation. Let's see if it is here. It's like finding the needle in a haystack. Let's see if I have it here. I insist for you to initial idea of how the original geometry looked like. Then we will kind of compare it and see how it looks now. So, for example, the actual version is this one. The simplified and optimized version is this one. In the meantime, I will do my best to present you the original geometry. Come on, Space Claim, please open. It opened. So the original geometry, this is the simplified geometry. Yeah, 2 stages. And somewhere here. So the purpose of this stream is to familiarize yourselves not only with joints, but also with very simple interaction, let's say, interaction in Explicit. Let's take a peek inside. No, it's not this one. Not this one. Maybe. Oh, not this one. Come on. Okay, so it's this one. Triple click. So I isolated only this shaft with this gear and this gear. Also this gear. And the input, I have used this gear as input. You'll understand in a few seconds. Let's hide them and Control A, or not. Let's just delete show all. These are what I selected. So this will be the input. Of course, I simplified, I removed the grooves from the spline shaft, and I applied some rounds. Hopefully you can see them here. Look here. We have rounds here. This is where we need rounds here. Sincerely, for this FEA, we don't need rounds at the base of the teeth, but I tried a very quick way to select all the rounds from the base, and it didn't work. So this gear has the rounds everywhere, let's say, while the other gears don't have rounds. So this is the actual geometry. Yeah, and this was the input, let's say. This here is what it was very thin. I made it thicker. I removed some rounds, which I deemed as not important. And of course, I solved some collisions, yes? So I rotated these in order not to have such collisions. For example, you see here, yes? While on the solved geometry, let me close here. This is the optimized geometry. There is no collision initially. Or maybe it is. What do you know? Let's kind of extract this just a little. Yeah, so we have no contact here, no collision, and here I'm interested. It seems like we have a collision here. Yeah, the simplest way is just to pull it outwards. Let's see if it is possible. 0.1, yes. All right. So yes, in order to verify if we have interference or collisions, we do have this prepare interference. And what do you know? There is interference. So let's kind of the geometry, the meshing teeth, so bottom line, the geometry is very complex. So pulling willy-nilly the gears is not, let's say, recommended. But yes, we don't want to spend too much time on this. Let's go with smaller values, 0.15 here. And I will go with 0.15 on the other axis. Look here on this axis. Yes. Of course, let's see what gives here. Prepare interference. All right. So it's settled. We're going to move this kind of like this. 0.1. And let's check the interference once again. Hide. Let's hide the parts that we don't need. I solidified these. I merged the shaft with these two gears. Let's look a little here. So 0.1 again. And let's see if we are out of the woods. It seems not. Let's make one gear transparent just for quicker to understand in a clearer way what happens here. Yeah, the only option I see is to pull the motor gear, the input, to pull it out. I don't see other option. Or there is the possibility of rotating, but I don't want to rotate it because it's kind of inclined, let's say. This is what we do when we have a geometry that we don't know. It's taken from GraphCAD, you know, it's not... and this is what happens with free stuff. Yes, it's you cannot rely on it very much. So let's pull it more outside. (0.1). We begin to have a collision here. Yeah, so mostly I would say that we're on the right path. So I can go here with 0.05 and again 0.05, and I would like to go here with 0.05. All right. Prepare interference. Oh, the slightest. All right. So design move and so I need to go on this direction with the small gear. Can I move this this shaft? Let's see. Yes, I can. I'd like also to pull this downwards to disengage more. 0.1. All right, so prepare interference. Nowhere else found. So there are no interfering bodies in the model. So we are very well. Only we need to pull this downwards with 0.1. Design, move, and 0.1. Perfect. Let's check again the interference within the entire assembly. Ah, we have an interference here. Okay. So let's also pull this outwards. It doesn't help. Pull it outwards. Come on, please don't. We need to carefully select the direction of disengagement, let's say. Curiosity, what will happen if I change this? Let me rename here width 4, save, and if I change the radius, for example, instead of 1, what will happen if I make it 1.5? Oh, yes. Only this will imply to change all the radiuses, let's say. Let's undo. Can I hope? Selection. All rounds. Let's make them 1.5 from the keyboard. I'm curious how they join here, the fillets. You know what? For the sake of this FEA, let's leave it like this. And check again for interference. There are no interfering bodies, yes? So we can close this. Dynamics. Yes. Let's delete this. I will have the default structure still, and we can go towards making the simulation. Let's see if is someone asking something. No. 0 odd. So we have the entire piece at our disposal to perform the simulation. So now it's being imported. In the background, the space claim is being opened. Yes. So because we are in there is no because. Let's deem this as input. This is output, and this is middle. I said rigid. Then we're going to delete the contacts. The only body interaction is frictionless. We will leave it like this. Let's assign some joints quickly. So this will be a body to ground Revolute joint. I'm talking about the input, the motor. Yeah, it would rotate about the z-axis. Another joint will be, again, a Revolute joint with the ground. You know, it's the ends of the shaft are usually in a bearing, and they are kind of rotating inside the walls of a housing, of a gearbox housing. So let's kind of take these two faces, even though one would have been enough, just for easier understanding. Let's assume this is in a housing, yes, and these are the. Here we have the bearings, which are embedded in the walls of the housing. And the third joint will be a simple Revolute joint. So this is what we have. Let's see how home units millimeters. Let's see how the mesh, a default mesh, how it will look like. $7,000 knots. Yes, it's kind of rough. It's very good for easier solving, but it's kind of rough. Let's get an idea about a thickness of a tooth around, yeah, around 0 and 5. So between 0 and 5, so maybe around 3.5. Let's leave it like this and generate mesh. We're going for the simplest options here. So it's better. Not the best, but it's kind of, it should be working. Let's go with 3. We do have a very coarse mesh here, so let's go with 3 millimeters. It's still coarse. Let's give it a run. Let's give it a run, you know. So 0.01 seconds. Let's say we do need a very short time for solving. Let's propose some time steps. We will leave mass scaling now at this moment. There is no inertia of eroded materials. Out of reflex, let's make it now, even though there is no erosion because we have rigid bodies. The only load that we have is the joint load, which is the first one. This is the motor. We will apply some rotations. Let's say, I don't know, 2 rotations. Let's apply 2 rotations here, and we will see the echo and the remaining of the assembly. So here I would like to see deformation, stress and strain not possible, deformation and velocity. And if possible, maybe some joint probe. Joint probe, we do know about the input. Let's see about the other ones, the other joints, what we can find. Forces, and for the second one, a moment, why not? Do I have everything to run? In principle, yes. Let's see if the FEA works. Four minutes, yeah, this would be nice. Why not? Instead of having a stream of a few hours, maybe we can make it, I don't know, half an hour. Let's see. Let's judge. So you see the red at the input, then it decreases, the deformation values decrease. Very nice, we like it. The bodies are rigid, this is why we don't care at this moment about the shape of the teeth. So let's go for our favorite segment, which is called Let's Get Inspiration from Others, ANSYS gears. I'm curious if this uses bonded contacts. This is a like for FEA, for beginners. Bonded contacts. Look here, what is this clearly? Here and here you can see from the naming. This is bonded contact. So use degree of usefulness 0. I don't care about the partial portions of the gears. Let's see here. Remote point. Oh my god. No modification of contacts. So I predict bonded contacts. What is this? Yes, so it's, of course, bonded contact or no separation. The common mistake. Oh, if these are teeth, then I'm an astronaut. And of course, I can bet that the contact is bonded. Yes? Can I bet? Yes. I can bet, no problem. Bonded contacts. This is why lubricant and oil is used in reducers and gearboxes to weld and to bond in place the teeth. It's sad and laughable at the same time. Let's see at least these helical gears. No separation. So, and 1, 2, 3, 4, 5, 6, 7 contacts. 1, 2, 3, 4, 5, 6. I would have removed the wedge here, the key. Yeah, no separation abandoned, and the result something awful, of course. Why not? Let's see this one. This should be interesting. It's from ANSYS files, from a training. So if this is a training, I think this person uses rigid dynamics because there is no contact. So go, run. Yeah, it looks correct. It's correct. It should be correct because it's taken from a training file, so it was made many times in the past by this person, I think. This looks complex. Let's see if it's correct. We don't need. Show us the contacts. Yes. Contacts. Frictional. Only one contact. So he has 1, 2, 3, 4, 5 pairs of possible contacts, 5 pairs of gears. And out of 5 pairs, only one is active, let's say. But here we have collisions. He included the second pair or what? Ah. Very few frames. This is a trick to use very few frames in order for people not to see the mistakes. Yeah, when you use less than 25 frames per second, which is a minimum decent animation speed, 25 frames per second. Here he uses 5 frames per second and nothing is distinguishable. We cannot say if what happens is correct or not. It's a single gear. So let's see, maybe it's everything now. It's solved, it fully solved, yes, and let's see. It's possible that some faces weren't taken into account. I don't know. Let's see. And this person, he or she, let's see, Parata. So he, what is this? So Mr. Barata made lots of FEA only. I hope they, after 8 years, I hope he evolved more than this stuff. If he stayed inside, then yeah, he evolved more. Let's see what's happening here. We're at the end. One second. So, ladies and gentlemen, let's see. Save. what I'm doing to achieve 25 frames per second, I make this 50, and 50 divided by 2 is 25. So this is clear. Let's go even more. 75 and 3. What I would like to see is to look for collisions. You have seen in the animations of other colleagues, either the contacts were bonded, either the teeth collided, and it was such a mess. Let's check those collisions here. 100 per. I don't know. Yeah. I don't know how well you can distinguish, but we can go here. For example, retrieve this result. There is no collision. And let's go and check collisions for other gear pairs. Look here. So there is no collision. Now here, retrieve this result. We advanced. There is no collision. And let's check for the other pair. No collision. Yes. Again, retrieve this result. No collision. No collision. For a nicer view, we have removed the, let's say, the edges of the elements, and yes, I would say it looks nice. Yeah, so let's check velocity, meters per second, for example. Then we have the total force in this joint, in both points of the bearings, which are usually embedded in the housing of the gearbox. Yeah, so we have variations due to the engagement of the teeth. The values are the peaks values are pretty high, because we do have some rigid parts here. Just out of curiosity, in order not to finish the stream so quickly, I will make the joints deformable, just out of curiosity, to see what happens then. Here we have the total moment on the output Revolute joint, let's say. It's 2 kilonewton meters, which is, I would say, it's very high. The peak at least, but we do have some smaller values. So the maximum is 1,000, 1 kilonewton meter. It's pretty big. What we can also see, if you would like, for worksheet here, we have the UV and VV, which are the vectors of displacement and velocity. Let's look at them. So let's make them bigger if possible, something like this. When having and evaluating such vectorial results, the evaluating of results is pretty slow. So this is why I input a faster animation, let's say. So this is the displacement tendency, and this is the velocity. Because the parts are rigid, there is nothing to be said regarding the stress and strain. Yeah, look here, they are. I can assign, but nothing will happen. If I am correct. Let's see. So as I said, stress 0 and strain 0. You know, it's we do have this equation, if you remember. And at this moment, let's say we have this one, the stiffness is infinite, yes? And this imposes 0, or I would say non-existent stress and strain in rigid bodies. All right, so I said something, and I would like to retire the fact that I was proposing to use the behavior deformable. I don't think it is possible with rigid parts, but because we do care about having a nice simulation, let's duplicate it in order to properly conserve it. And let's make any changes in the new simulation. Command duplicate. Why does it take so long? Why? So it doesn't seem busy. So let's use this for tests. So as I was saying, even though it's kind of absurd, let's make all these here the behavior of rigid and mobile. Let's make them deformable, even though I think it's not possible. And let's see what will happen. Maybe it is possible. If it is possible, then the parts will disengage, will fly away, I think. Let's save, then solve. It looks like it's going to solve. Only we need to repeat the solve command until it works. We're looking for errors here, but because everything is complete, then we're on the right path towards solving. Solve. So in FEA, we need lots of patience, as it is the thing for most important things in life. Yes, we need patience. So it does work. Let's see what gives. Yeah, kind of nothing. Let's look on the. No, nothing happens. Yes. So yeah, it's absurd to use deformable for rigid parts. I was thinking about using deformable only for mobile side, but no, it makes no sense. So here we have it. What I will also try is, even though I don't think we can solve it in this stream, I have tested it last night. I will try and make this flexible. And this opens a new can of worms. So let's make all the parts flexible, and we will see what problems we encounter. Save. Solve. We do have some error, energy error. Let's see what says. Energy error too large, yes. So let's go for this simulation. Let's make this 0. Save. Solve. So instead of 4 minutes, it went towards 4 hours, which I would say is not so funny, especially when having a live stream. And if someone would be crazy enough to wait 4 hours, maybe the results will not be so funny. I mean, so realistic and reliable. Let's apply some mass scaling. In order to heavily decrease the solving time. I cannot make the mesh coarser because we already have very coarse mesh. what should I do? Thinking about making a sphere of influence here and a sphere of influence here. So we have 62,000 nodes. All right, 4 hours, 4.5 of solving. Let's go here with the mass scaling, 1e minus 7. Let's try with 7. Save and solve. It will work, of course. What I would like to do is for erosion controls, no. Geometric steel limit, it's kind of too much for steel. I don't know, maybe 1.2. And this is default steel. This is the linear elastic steel. There is no plasticity. Let's go with this. Solve. If things work all right, we can assign nonlinear structure steel from engineering data. Only then the entire assembly will become softer, let's say. So now we have two directions to decrease the solving time. We're going to increase the time step. Yeah, to increase means -7, -6. And we can also make a coarser mesh in the parts that we're not interested. 1.3 hours, it's not fun. It's 3 times smaller than what we had before. And let's increase the Courant-Friedrichs-Lewy time step. Yeah, CFL. Courant-Friedrichs-Lewy, from the 3 mathematicians which proposed this option to decrease the solving time. All right, so let's delete a 0, 1e minus 6. And if I am correct, maximum part scaling, the default value will not work. Look here. So we will need to increase maximum part scaling, I think. Yes. So mass scaling limit exceeded for blah blah, all 3 parts, 26, 11, and 16. The easiest way to solve this may be assign 15. Does it work? Clear generated data, save, solve. Is there someone to say hello? Yes. Hi, Jose. Jose Ronaldo Perez. Beautiful, kind of beautiful, yes. Hermosa, no? Hermosa. Thanks for watching. So, where were we? It will work. So we now have 3 people in our large audience. Everything is better than 0, yes? So in this live stream, we're checking how we can simulate an assembly of gears using Explicit dynamics. And you can see some tricks that I know from experience in order to make this FEA work and then solve faster. Because you can solve it in 4 hours by default, but you want to solve it in maximum, I don't know, 20, 30 minutes. And for this, you need experience in Explicit dynamics in order to know how to decrease the solving time. So if you have any questions, please feel free to ask them in the chat. And as a reminder, in a few weeks, I will open or publish my Patreon account, and there you can watch and you can access the files, the geometry files and the simulation files for these live streams, and for other webinars there will be some free simulations, and for the members of Patrons, which will be a very cheap solution. In order not to pay, I don't know, $20, $30, $50, $60 for 2, 3, 4 simulations, you'll be able to pay, I don't know, maybe around $10, $15 and get access to lots of FEA stuff in a bundle all at once. So yes, it will be very useful for people who want to improve and perfect their simulation skills in ANSYS Workbench, and for people who would like to have a career in this field, not necessarily in ANSYS, but also the same principles apply to other FEA software. But ANSYS, Workbench ANSYS products, they are a very good start in this world. I know from experience that this will not solve. Let me see if I can stop it. Having this message will not solve, but in the end, of course, this simulation will successfully end. We need to find the solving executable, yes, which is something like AutoDin. Let's see if I can find it. No. Here. So ANSYS solvers, yes, and task, and the solving will hopefully stop. Yes. Clear generated data, yes. Solve. So feel free to benefit from my knowledge, and if you have some questions, especially regarding the structure side of ANSYS Workbench, then I think I can help. If not, I will point you in the right direction. Also, remember, we are in the age of AI. Remember to ask AI even the most, let's say, the questions that you think are most stupid. Ask AI, because the AI will not mock you and nobody will laugh. So ask, and the AI will guide you readily. Not without error, of course, because I have experienced some ill advices, let's say, from AI. Come on. AutoDin wrapper. I don't see any solving here. Let's end task. Yes. Do you have any questions from the audience? What system specifications are you simulating? Mr. Jagpreet Mude, I think is a Mr. This one. So I invested some money in the processor, and yes, it's the processor is good. Okay, considering the fact that I'm at home. Yes, I'm a home user. Yes. The RAM, until now, I didn't find the use of having more RAM. What I will advise is to have only NVMe drives, because the result of the solving, yeah, the files are written on the so-called hard drive. Now it's solid state drive, and go for last generations of NVMe, at least 4 or 5, which will ensure a writing speed of 2, 3, 4, 5, 6, 7, 10 gigabytes per second. Don't use hard drives, which are limited to maybe around 50, 70 megabytes per second. So go for NVMe, yes. And the card, I don't know if it's so relevant. I was so blessed because I purchased the card a few 2-3 months before the craziness with the RAM that's happening now. And yes, so the card is very recent. And the memory, I made an upgrade exactly 1 month, I think, before the RAM price increase. So now I have 128. And the fact that I have a Coarse that can go upwards to maybe 4.2 gigahertz, this helps very much. So of course I don't need to overclock it, and it's never my intention to force a system that works very nicely. What I said maybe 5 minutes ago, I said that this maximum par scaling would not be enough, and I was right, because look at this these mass scaling error messages, and they are easily solved with, I don't know, let's make it double, almost double, 35. Clear generated data, yes, safe. And of course, my display is pretty big. It's 43 inches because I like to rotate and see in details all the errors and the small elements. So this is what I advise, yes. I advise to have at least, for a desktop computer, at least maybe 24 cores, maybe at least 64 gigabytes of RAM, and 1 fast NVMe drive. Yes, the latest, I think, generation 5 runs at about 12 gigabytes per second, which is extraordinary. So this is all I recommend. And of course, depending on your eyes, bigger screen if you want. The graphics card is not so important. I wanted to have it, yeah, because I'm using Discovery. The Discovery suite in ANSYS uses NVIDIA graphics card. This is why I'm kind of bound, and I like being bound by the NVIDIA video cards. Also because I use the Discovery suite of software. And it solves using the GPU. Yeah, holy fish. Yes, yeah. If you need it, if you can, why not? Invest if you see a future. Why not? So we're going towards the much coveted 30 minutes that I wanted. So I can live with this. We will maybe spend some time looking at other simulations from other colleagues on YouTube, and maybe at half the simulation, if it goes well, maybe we will interrupt. But I predict that changing from rigid to flexible, I predict there will be some problems. Look here. So, for example, this big gear is being abnormally deformed, yes? This is what I was kind of predicting. So what we do at this moment is we interrupt the simulation. And make somehow force this gear not to displace on axially, let's say, if we can say, axially regarding this shaft, yes? So let's make here 0, and I would like to propose to have a displacement of this and this. Let's make it the y-axis is the, I don't know if you can see it, look here, is the longitudinal axis of the shaft, yes? So let's make this 0, and let's see if it works. I was suggesting like a sphere of influence. Look here, I'd like for you to retain this method of making the mesh more coarse. In this case, it will be more coarse. Look here. I will click here and create a coordinate system. Yes. And that coordinate system, this one, I will be using it here with the sphere of influence. Sphere center will be not the absolute coordinate system, but the relative one, which we just created, this one. Let's click this part because it's needed. And sphere radius, I would like to have a radius kind of equal with to the radius of this gear. The radius of this gear is, let's assign millimeters, around 75 millimeters. So let's make it 80, yeah, something like this. Why? Because we need only the teeth to be fine as mesh. Yeah, the crown, let's say, but not inside. Inside we need to be as coarse as possible. 85, is it better? Yeah, kind of, but it goes here, so let's make it a little smaller, something like this. Maybe 83, maybe 83. All right, so this portion I would like it to be coarse. Coarse, I mean 5.5, for example. And let's do the same here. I will create a coordinate system, Control F here. Let's move. Do we need to move it downwards? We can move it downwards. Look how we move it downwards. Yes, there is coordinate systems here, offset y, and it will be with plus. How much? Maybe around 10 millimeters to move it downwards, let's say. So 10 millimeters. It's kind of too much. Let's make it 5, and this is all. Yes. So I will use this again as a sphere of influence for this sizing. Control B for it. And I will say, instead of type element size, I will say sphere of influence, sphere center, the second one. And you will see in a few seconds what is the radius of this gear, around 40 millimeters. Yeah, This is something like this. 42, maybe something like this. And again, 5.5. So I would like to make the center or the inner portion more coarse in order to decrease the solving time. Any other question? No. Okay. So let's do the same for this gear. What I'm doing, I'm selecting both of these, and when I click the coordinate system button, it will be assigned exactly at the middle, yeah, between these surfaces that I clicked on, yes, that I selected. Look here, exactly like the middle. Let's do the same. I can duplicate here, select coordinate system 3, and the radius of this gear is around 20. Even higher. 25, 26. All right. Something like this, maybe 24. I don't want to have the teeth there. You'll see in a section view, I'll make some section views in order for you to see the difference between the coarse and fine mesh. Save. And let's see 2000. Now we will have how much? My aim is to go towards 40,000, 40, 45. Oh, 29. Why not? Why not? Small question. I think I exaggerated here, and this is why we have coarse and fine, because the sphere of influence kind of overlaps here, and it touches the teeth. So I would like here the diameter, the radius 41, and let's generate mesh again. It's, I think it will work good. Let's leave it like this. Because the next thing, we would like to see if the blockade that we assigned axially, we'd like to fit if it works, yes? Let's make 0.005 and assign maybe 1 rotation, yes. We're doing anything and everything to decrease the solving time, while in the meantime checking what problems might occur. So there is a problem here, getting boundary conditions. This is a problem. I think this face might collide, or maybe it's too close to this face. You know what? Let's scope only this outer face, because maybe this face collided with this joint. Maybe, I don't know. Let's see if now it will solve. So we have a very good solving time. Now let's see if the behavior is correct. It does not look good. It does not look good at all. Yeah, let's judge the energy conservation. No. Not correct. We need to have increasing work and total energy. So no. Let's test something. Can I dare to make here and here the Revolute joint? Let's see if I dare. Then this would mean maybe I can change this face here and not leave it, not allow it to move axially regarding the y-axis. Let's see if it works. If this does not work, I will make this part rigid, and yes, that's all. Will not spend too much time on proof of concept. So it will work. I pointed out the fact that we have no errors there. Let's solve. Come on, solve. Please solve today. Oh, beginning. Let's see if it behaves correctly. No. I'm wondering about the fact that I made the mesh coarser. Maybe this affected the simulation. So let's just interrupt. And let's make this rigid. When we have a rigid body, we need to select the entire body, not only one face. This is why we are going for body. Let's suppress, maybe it's not needed because it wasn't needed in the past. Yeah, so we'll have a mixed simulation with rigid and flexible parts. Does it work? Yes, there is no error, so in the end it will solve. So it might not work. Yes. So we're drawing the conclusion that maybe the mesh coarseness, maybe it didn't help, but it did the opposite maybe. So let's go here and let's suppress. So we're back to 62,000 nodes, I think, 60,000 nodes, all right. And I'll be keeping the middle as rigid. Save and solve. We don't have any loads. It cannot rotate anything, so I don't know how I missed this. It should have divided. We have 360 degrees, it should have been half, 180 degrees. So false alarm, let's keep this. And sign here, 360 degrees. Save. And solve. We need to be very curious and inquisitive. We need to look everywhere for potential errors. So 7 minutes or 6. Let's judge the energy conservation. Yes, this is more like it. Solver output and right click, adjust to visible, and it looks very nice. Even though the teeth are crooked due to the coarse mesh, it looks nice. Let's assign a stress because it will be applied on the flexible bodies, the input and the output gear. Only a small problem is the fact that we didn't use a nonlinear. This is why we do have some pretty big values. It makes not much sense, so we definitely need to change the material to be nonlinear, and because these are not all right, look here how they run. Maybe we'll need a finer mesh, you know. But for today's purpose, where we should be. So let's leave it solved. Then I will replace the linear steel with nonlinear steel. How much does it take? 5 minutes. All right. So where are we? Any question? We have. Привет, здравствуйте, Mr. Alex. Hello. Nice seeing you here. So let's look at our other colleagues. Yes, 10 years ago. Let's see what people did 10 years ago. Yeah, very nice modeling. Let's see the simulation. Frictionless. Frictionless is nice. If it rotates, then look here, the problem. 140 scale. So this person is watching. Yeah, it's good. And go, animate. He didn't apply filets, so he has sharp edges on the teeth heads, let's say. Sharp edges, which is not advisable or allowable. And let's check a little the stress. 2.5 psi. $1,700. Yeah, so it's clear for me that this is a linear steel. Now I'm seeing. Yeah, it's linear. Look here. It's first time. It might be the first time when I see a 2D gear simulation. So I give him props for doing this. even though, yeah, it could have been extended and improved. But yeah, it's a good work. How many minutes? Just visible, yes, and as I said, we will be changing the structure steel without plasticity with the nonlinear one, which allows plasticity, and that might change the paradigm of the simulation. This looks nice, only I think it's not so. So no value, no, it's something from fatigue, from static structure. The contacts, of course, are bonded, I think, so degree of usefulness almost zero. Rotating helical gear shows the entire gear, not only portions. Analysis de engranes, what? Come on, open. So in Spanish, I think should have been engranaje, not engranes, yes? So with my little Spanish, yes? Engranaje. Oh, the mesh is so coarse, oh my god. But if it works, yes, all my respects. I'm curious about the contacts. Bonded. Will it be bonded? What? He left it bonded, so degree of usefulness 0. Design of helical gear in ANSYS space claim. ANSYS space claim is written one word here. Spur gear. Judging from the deformation of the teeth. Share my video instead of video. Why should someone share this? Let's see the bonded contact. Yes, yes, bonded contact. And it's left like this, yes? It touches only two faces. And bonding contact. So, yeah. And the result is nothing. Of course, also because almost 4,000 scale. And it's sad and laughable at the same time. Armin Hashem, intermeshing gears with contacts. Finally, something that looks nice. One gear is rigid and one is flexible, if I say correctly. I think this is something good. So, good luck watching. And assist tutorial edges dynamics. Oh, yes. Intermeshing gears, Revolute, joints and joint product. Yeah, this looks nice. Designer modular. This thing does not exist. There is something called design modular, but not what is this. This is taken from one of my simulations. Let's see how it looks like in the end. Then let's try with the, as I said, with nonlinear steel. There is some rattling, let's say, here in this output here. As I promised my audience, let's assign a steel with plasticity defined. Gear damage analysis using ANSYS Workbench static simulation. You cannot find damage on static. No, damage is a measure, an output. It exists only in explicit dynamics when we assign materials with Johnson-Cook parameters. So I will be here flexible plus rigid. Here I will say all, and here we will say NL steel, nonlinear steel. All right. Also flexible and rigid. So as I said, let's delete this and see what changes the linear materials induce in our simulation. So I accessed this library, general nonlinear materials. The thing that is additional, let's say, with the general materials is when we look at the structure steel, we only have isotropic elasticity defined here. Yeah. So this is a line, let's say, on the stress strain curve. And here, when we look at general nonlinear materials, structure steel nonlinear, we do see bilinear isotropic hardening, which describes what happens after the yield point. Yeah, this is the plastic domain. And we have plasticity allowed until breakage occurs. So double click here, open. What? Science metaverse. So it looks bonded to me. Yeah, it's bonded. This is a disgrace for the Indian people. CAD manufacturing. Why do you present something like this? Why? Why? Bonded contacts. And there are Indian people who are very talented and they present so nice simulations, and this is also taken from one of my simulations. The name is familiar. I think he's one of my customers. This is so nice. I need to see it. So we have question mark because everything should be structured. Structure still nonlinear. Where is structure still nonlinear? What? All right, let's take it as a bug. Let's see what changes we have. Now we should not have any 10, 20,000 megapascals, yes? Because we have plasticity allowed, and we have something like a max, like an ultimate tensile stress defined inside this bilinear isotropic hardening, let's say. So it looks nice here. It will solve, I think. All right, let's solve again and again. Come on. Why responded? Klaus, can you switch to a lower display scale during live? Low resolution. This text in ANSYS can barely be read. Sincerely, I have watched my videos and they are readable. So, Alex, as much as I care about you and your eyes, I didn't have this complaint until now. Maybe you're watching on a small laptop, on a small display with a very high resolution, and maybe this is why it's not visible. But believe me, I've watched my videos, and it's readable. So I will ask a question from other people. Can you read the text in ANSYS? Please answer in chat if possible. If you can read the text that you see here. ANSYS settings, deformation, stress, strain. Please, I'm curious, like a feedback if you can answer. Meanwhile, we have something like this. Why used bonded? Yes, because of lack of experience. I will not say something bad, but it's absurd. Yeah, and the contact should be, if not frictionless, should be a frictional with very small friction coefficient, maybe 0.01, 0.025. Bonded is absurd and it's laughable, and this is a product of lacking knowledge, common sense, and experience, lacking everything. And pretty simply, I was thinking about not caring. It's more than not caring. When introducing a nonlinear contact, and frictional and frictionless are nonlinear contacts, the solving problems appear. So this is your answer. Bonded contacts ensure convergence, even though it's stupid and useless. And this is where the line is drawn between advanced people and beginners. The line is drawn when using exclusively bonded contacts, then using frictionless and frictional. So let's see what will happen here. Let's change this to millimeters and right-click, adjust to visible. Yeah, it looks nice. And you will see the fact that, oh, look here, the effect of nonlinear. So it became softer, yes? The teeth became softer. The problem is the fact that we have a very short span, yeah, of time. Look here, it's millisecond. And when we apply a shock, this is a shock for this amount of time. When we apply a shock, it will go towards the flexible component. This is our flexible component. This is rigid. We remember the one in the middle is rigid. And it behaves, let's say, erratically or spurious, as other people would say. So yeah, this is one of the effects of having nonlinear materials. So the parts become much softer. Just a reminder, yes, to be taken into account. I will let it solve, even though I'll not use this, I will not publish. I will publish one of the previous simulations. So yeah, look here. So this is rigid, and I hope this is not a collision, I hope, but it is. It gravely impacts the soft part. Yeah, the rigid one. I can. So if I had more time in this live stream, I would have increased the end time. Normally 10 times this value would solve this, will ease the initial shock. If we have a bigger end time, where we will be close to reality. Then what I would do is make also this part, which contains all this. I'll make this part flexible. So if I were to increase the end time, then we will need to have a solving time of at least 1 hour, which is not feasible for our live stream. But you understand my ideas, yes? So what is to be done next is increase the end time, solve, see if the shock has loosened or disappeared. Then, if needed, make also this middle part, the middle so-called subassembly, make it also flexible. I'm contemplating making this part flexible. I'm contemplating this idea. You know what? Let's make it flexible because this FEA, of course, it's not usable. Let's make it flexible, then end the live stream. So, to my current audience, if you have questions, advice or something, I can hopefully point you in the right directions regarding mainly ANSYS and FEAs. What I was saying is let's save it. Why not? Because it's work, and work needs to be saved and conserved. Let's duplicate here and make everything flexible. Do we have AI? Ah, no. Perfect. So feel free to ask FEA questions if you have some, I don't know, queries, or maybe ask about a future job or what you need to know. I might be of help, you know. So here is all flexible. There is a comma at the end. I don't know who put this comma. All right. I promised to do this to make it flexible. And let's, you know what? Let's double this 0.01, or let's triple it. I would like to loosen and to decrease the initial shock of the motor. This is where we have the motor gear. So we'll go towards 18, 20 minutes of solving. And I'm interested on how the teeth will behave, if they will bend so much as in the past. So it's nice, it will solve. Control S, solve. This takes time to load. Let's delete this. Solve. So nobody forces you to watch all these trials, but of course you'll be missing some hints and tips and tricks here and there, which tips and tricks come from years of experience. So suit yourself, choose what you need the most. Let's watch a little other people's work. Very nice, work of art. Why shouldn't the arrows be the opposite way? Yeah, it should be, I think, in the opposite direction. But who am I to ask? So this person made a short video out of a big webinar or training video and sped it up. One gear is rigid and one gear is flexible, I think. And yeah, it kind of looks nice. Oh, even though it's so quickly sped up that it's almost incomprehensible. This looks nice. Mr. Dmitry Kalinin, I think I've seen some of his work. These gears are laughable. On gear and pinion. Let's see. What? Yeah, very nice. Yeah, very nice. Finally, some good work. Does he have more? Ah, only 2 free simulations. All right. Very nice. I would have filtered with maybe 500 megapascals to see more of the stress. Very, very, very good work. Очень хорошо. Rigid dynamics, double helical gears. It looks nice. Is it correct? It's not helical gears. They are called herringbone gears. I have done something similar in the past. So, yeah. This is nice. Yeah, this appeared after I published a similar scenario. So this person, I'm most certain he took inspiration from my work. Yeah, this is what I was talking about, herringbone gears. So what do we have here? It's kind of nice, only it's getting out. The same problem with the displacement. So this gear is getting kind of bended. Or bent. Let's assign a formissive stress solution. So look at values. Nice values, yes? So 300. Nice values, yes. What we need to do now, if possible, is last thing. Let's assign on this face zero displacement. Yes? Zero axial displacement. Let's see if it works. And we're approaching the end of the stream. I'm trying to compensate with the FEA the fact that in reality there are walls, there are bearings, there are bushings, there are many parts to properly assemble and support these gears. So because I'm using only the principle, only the gears, I need to compensate the lack of supports. Come on. Solve. This error is laughable and sad. My quote. Laughable and sad at the same time. But we need patience, and this is the difference between someone who quits very soon and someone who never quits. So this is what I have done a few years ago. How much? 4 years ago. Yeah, very, very nicely done. I say this with all my modesty. Kinetic energy. This is a force reaction. Strain in the teeth. Gap in the contacts. Potential energy. Oh my god. Alright, so this is what we call curved cycloidal teeth rack meshing with gear. So what you can see my simulations, no collisions, no interferences, no body contact. So we're describing the reality, not something that is useless. Come on. Why do you do it? Fine. All right, so where was I here? Yeah, it looks so nice. Failure is not written like this. What? ANSYS CFX. This should be nice if it works. It looks like SPH, smooth particle hydrodynamics. Cat engineer, so there's a cat involved. Let's see what the cat can do. Cat can do. So it's kind of promising. Only the teeth. I can see that the teeth will be. Yes, you see that they're extended beyond the gear periphery. Let's say so. Let's The teeth are pretty well bent, which is not very useful. Let's filter with 1 maybe, yes, and we will see how the displacement propagates. Just too visible, and here, let's look at stress. Yes. Oh. Maybe we should change the rotation direction, maybe. So this being said and done, we do have something, yes? We have seen lots of solutions and ideas. Oh, here is getting out. Yes, so we have seen some tricks. So I propose to end the lecture here. I will admit that this simulation is going nowhere, but we have other things from the past. Past of this simulation, namely, I would like to remind you about this simulation, I think. This one, yes. Because I'd like to end on an optimistic note. So here, let's animate just a little for fun. Yeah, there is a tendency, it's getting out. We should better constrain and support the parts, but of course, these need to be done in days and weeks of work, not in 2 hours of live stream. So I will end on this optimistic note. This one. I like this, stopping this. So let's end with this because it looks so nice. Oh my God. This is all from my side, ladies and gentlemen. Let's see if we have any other questions. I don't see any other questions. So thank you. See you next time. Good luck in your FEA endeavors and adventures. Bye-bye.